Chapter 10, Section 1, Energy and Work. Energy is the ability of an object to produce a change in itself or the environment. Moving an object, changing its, which is the change in position, is one example. It could also be thermal energy, chemical energy, or the energy of motion, which is, of course, called kinetic energy. This is one of those things that we learned all about in physical science. So our equation is the same. It has not changed. Kinetic energy equals 1/2 mv squared. M, of course, is for mass, and we do need to make sure it is in kilograms. V is velocity, and it needs to be measured in meters per second. The process of changing energy of the system is known as work. And work is calculated with this equation. Work equals force times distance. Force is represented with the F, and it is measured in newtons. And D is for distance, and we need to make sure distance is in meters. W is the symbol we use for work. When work is done on an object, its kinetic energy changes. So we have the work done equals the change in kinetic energy, and this is called the work energy theorem. Work and energy are both measured in joules, which is a unit named after James Prescott Joule. What else do we need to know? Whenever we do work on an object, we change its kinetic energy. So we need to make sure that the force that we use in our equation is in the same direction as the motion. That is an important point. And other than that, we can look at this first example problem. A 105-gram hockey puck is sliding across the ice. A player exerts a constant 4.5 Newton force over a distance of 0.15 meters. How much work does the player do on the puck? What is the change in the puck's energy? So our mass is 105 grams, which we do need to use as kilograms. We have a force of 0.45 newtons, and our distance is 0.15 meters. How much work does the player do on the puck? So work is force times distance. So we're going to take 4.5 times 0.15 to find the work. Our work is 0.675 joules. What is the change in the puck's energy? The second question. Because the change in kinetic energy equals the work due to the work energy theorem. Since we know the work, it is also equivalent to the amount of kinetic energy. The next page is 5 problems for you to do on your own. 1, 2, 3, 4, 5, all using the work equation and or the kinetic energy equation. All right, constant force at an angle. As discussed previously, we want to make sure when we're calculating work, the force has to be in the same direction as the movement. And so if we look at the 125 Newton force at a 22-degree angle. So here's our box, and we have a force that's 125 newtons, but it's at a 22-degree angle. We cannot use the whole 125 Newton force. We have to first break the 125 Newton force into its components. And we are going to use the cosine function. We don't care so much about the force in the y direction because our box is going to be moving only in the x direction. So we want the x component of the force because our movement is in the x direction as well. So that's going to change our calculations just a little bit. Looking at this example problem, a sailor pulls a boat 30 meters along a dock using a rope that makes a 25-degree angle with the horizontal. So here is our boat and the rope, and it makes a 25-degree angle with the horizontal. So there's 25 degrees. Our distance is 30 meters, and the force exerted on the rope is 255 newtons. Again, we're not going to use that whole force. We only want the x component of that force. So if we draw a right triangle, 255 is our hypotenuse. We want the x component of that. Our angle is 25 degrees. So if we are solving for the x component, we're going to use cosine. Cosine of 25 equals fx because it's adjacent over hypotenuse. So our x component of the force is 252.7 newtons. And so once we have that number, we can then use it to calculate our work. Work equals force times distance. Force is 252.7 times 30. So the work done on the boat is 7,582.7 joules. And there are 3 problems for you to do on on your own. The last section, or last part of section 1 is power. Power is the rate over which work is done, and we have an equation, work divided by time. This all goes back to the fact that work has nothing to do with time. So if you have a box of books, you're going to do the same amount of work if you lift the whole box in 2 seconds, or if you take each book out separately and it takes you 20 minutes to do it. The work you do is the same, but the power transferred is different because power involves time. Power is also measured in watts. 1 watt is a joule per second. So we want to make sure our time, when we work problems, we want to make sure our time is in seconds, measured in seconds. Again, kilowatts is probably more commonly seen because 1 watt is very small. So for the example problem here, we have an electric motor lifts an elevator 9 meters. So our distance is 9 in 15 seconds. Time is 15 by exerting an upward force of 1.2 times 10 to the 4th newtons. What power does the motor produce in watts and in kilowatts? So our power equation is work divided by time. In this problem, we're going to have to calculate work first and then find power, or we can plug in the work equation in for the W. So force times distance divided by time. And that'll save us one step. So I plug in what I know, 1 times 2 times 10 to the 4th times 9 divided by 15, which is 7,200 watts. That answer in kilowatts would be 7.2 kilowatts because there's 1,000 watts in 1 kilowatt. And there are next 4 problems calculating power for you to do.